Okay, picture this. You've just built an AI model. In the laboratory, it is absolutely flawless. I mean, it's predicting every single data point, it's acing every test, and it looks completely ready for deployment. But the very second it leaves that perfectly controlled environment and hits the real world, it completely falls apart. It makes these baffling, almost embarrassing mistakes and totally loses its predictive power. And this is a massive deal, because these are the exact types of models driving the apps, the recommendations, and the tools that we rely on every single day. So welcome to this explainer. Today we're going to unpack exactly why this happens, and more importantly, how data scientists actually fix it. Let's get into it. So what's actually going on here? Why do these seemingly perfect models just crash and burn in reality? Well, whenever an AI fails to make that jump from the lab to the real world, we are almost always dealing with two hidden culprits. I like to call them the oversimplifier and the overthinker. These two opposing forces are basically in a constant tug-of-war inside any learning algorithm, and if you leave them unchecked, they will secretly destroy your AI's predictive power. Here is our game plan for today. We'll start with the AI balancing act, then dive into bias, then variance, explore the trade-off between the two, and finally, wrap up with how we actually tame these extremes. Kicking things off with Section 1, the AI Balancing Act. Look, the absolute holy grail for any machine learning model isn't just to memorize its practice data. The real goal is to generalize robustly to entirely unseen real-world data. Which brings us to our first major hurdle, Section 2, bias, or as we called it earlier, the oversimplifier. Now, real quick, in the data science world, bias isn't about unfairness or social prejudice. We're talking strictly math here. It's the error that gets introduced when you try to approximate a highly complex, real-world problem using a model that is just way too simplistic. The core issue with a high-bias model is that it basically ignores the training data. It is so ridiculously rigid in its assumptions that it totally misses the crucial underlying patterns that are staring it right in the face. To really picture this, imagine you're trying to map out the trajectory of a massive roller coaster. You've got complex loops, massive dips, sharp curves, the whole shebang. But your AI model is forced to use a single, rigid, straight ruler to draw the path. I mean, good luck with that, right? That straight-line model is trying to predict highly complex, nonlinear data, and it's just too basic for the job. Because of that extreme oversimplification, your predictions are going to be wildly off the actual track. If you're a developer staring at your metrics, the symptoms of high bias are actually pretty easy to spot. The model oversimplifies everything, which means it completely fails to capture those deeper patterns. And the ultimate smoking gun, you're going to see massive inaccuracies and really high error rates on both your training dataset and your test dataset. When a model suffers from this level of extreme simplicity, we call this real-world failure underfitting. It literally just hasn't learned enough. But what happens if we swing the pendulum all the way to the other side? Let's move to Section 3, variance, the overthinker. If bias is the stubborn model that refuses to learn the details, variance is the model that overthinks and memorizes absolutely everything it touches. Variance is basically a measure of a model's extreme sensitivity to tiny random fluctuations in the training data. High variance models are highly tuned. Actually, scratch that, they are completely overtuned. Instead of learning the actual signal, they obsess over random noise, weird outliers, and random sampling errors. It's kind of like an overcaffeinated student who is just hyperfixating on every single irrelevant detail. Which perfectly sets up the exam analogy. Imagine a student cramming for finals. If they ruthlessly memorize every single answer to a sample practice test, down to the exact phrasing, maybe even memorizing the typos, they are absolutely going to score 100% on a practice run. But what happens on exam day when the professor slightly changes the wording of a question? The student totally panics and fails. That is high variance. The AI memorized the training data perfectly, but it has literally zero ability to generalize when it sees something brand new. So let's look at these two extremes side by side. On the left, we've got a model that is way too simple. That's high bias, which leads to underfitting. It's just completely missing the point. On the right, we have a model that is way too complex. That's high variance, which leads to overfitting. It's captured all the signal, but also all the useless noise. Finding the sweet spot between these two, that is the absolute core challenge of model design. And that brings us to the climax of this whole explainer. Section 4. The Bias-Variance Tradeoff. Because here is the harsh, unavoidable mathematical reality. Achieving zero error across both of those extremes at the same time is impossible. It just can't be done. As the foundational formula shows, your total error equals your bias squared plus your variance plus something called irreducible error. Your total error is literally a balancing act of these distinct components. Think of it like a pie chart where bias and variance share a finite amount of space. It's basically a game of whack-a-mole. If you push one down, you almost always force the other one up. Decrease your model's complexity to lower the variance, boom, your bias shoots up. Increase complexity to lower your bias, suddenly your variance is through the roof. Minimizing both perfectly is a complete myth in practice. You are always trading one off against the other.
But wait, what about that third piece of the puzzle? This is super fascinating. It's called irreducible error. This represents the inherent noise in the universe itself. Let's face it, sometimes data is just messy. Sensors have static, human behavior is totally unpredictable, measurements have physical limits. This type of error absolutely cannot be eliminated no matter how insanely complex or perfectly tuned your algorithm is. A literal perfect score of 0 error? Scientifically impossible.
Data scientists love using the bullseye analogy to visualize this. Imagine you're throwing darts, and the center is a perfect prediction. If your model has high bias, your darts are clustered really tightly together, but they're way off in the top corner of the board. You're consistent, but consistently wrong. Now, if your model has high variance, your darts are generally centered around the bullseye, but they are scattered wildly all over the place. What you actually want is a tight cluster of darts right in the dead center. Low bias and low variance. So how do we actually pull that off? Let's get into Section 5, Taming the Extremes, and look at the practical toolkit we use to find that Goldilocks zone. Your strategy here depends entirely on the symptoms your AI is exhibiting. Let's say you need to prevent overfitting, meaning your variance is way too high. You've got to simplify your architecture. You can use a technique called dropout, which literally randomly turns off neurons during training so the AI doesn't get overly reliant on specific pathways. You can also use regularization to rein it in. On the flip side, if you're battling underfitting, meaning high bias, you have to give the model more brain power. You increase complexity by adding more layers to your neural network, training it for longer epochs, and pulling richer features out of your raw data. But how do you know which disease your AI actually has in the first place? Well, developers diagnose this by closely monitoring the gap between training error and validation error. If your training error is super low but your validation error is ridiculously high, that massive gap is screaming overfitting. Your model just memorized the test. But if the error is terribly high on both training and validation, that's underfitting. Your model is just way too simple. You find that gap, and you dial your model's complexity up or down accordingly. Now, these challenges get absolutely wild when you're working in low data scenarios. When data is scarce, the risk of your model just memorizing noise is completely off the charts. To survive this, developers have to get really clever. They use data augmentation, like flipping images upside down or back-translating text, to artificially create synthetic data. They use k-fold cross-validation to test the model on different rotating chunks of the data they do have. And they use incredibly strict, judicious regularization to keep the model from going off the rails. Which kind of leaves us with a massive philosophical question. We know we can balance bias, we know we can manage variance, but remember that third piece of the puzzle? If irreducible error is just a fundamental, baked-in property of a messy universe, will we ever achieve a truly perfect AI? Or is the ultimate pursuit of machine learning not really about achieving perfection at all, but just mastering the art of the trade-off? Definitely something to think about the next time an algorithm makes a totally surprising prediction for you. Thanks so much for joining me on this explainer, and I'll see you in the next one.